basically it's a shortcut. We don't have to write so many long numbers, you write it shorter, and then when you do actual operations, multiplying it and dividing it, it's much easier to divide the scientific notation, because it's little, than to divide like billions and trillions and quintillions and stuff, right? It's long numbers. So, if we have a positive exponent, this tells us how many places to move the decimal. To the right. And a negative exponent tells us how many places to move the decimal to the left. Okay, same as on another one. Okay, so 2.6 times 10 to the 7th. It's telling me 7 decimal places from that 2.6. So I've got my decimal right there. I'm going to go 1, 2, 3, 4, 5, 6, 7. And fill those up with zeros. Okay. Gives me 26 million like that. If you don't want to draw the squiggly wavy lines, there's another way to do this. I start counting at the decimal place. And I need to count to the 7. So I go 1, 2, 3, 4, 5, 6, 7. Like that. So if there were 2 decimal places, so if it was like 6, 5, I'd go the 6 for 1, the 5 for 2, and then add zeros up until 7. So yeah. So 2 different ways. You can draw squiggly, loopy things and then fill them with empty ones with zeros, or you can count off your places. And when you do the same thing with the negative exponent, you just have to count them off and move backwards, basically. So on the 1.1 times 10 to the negative 4th, with the looping method, you want to, if you have a negative exponent, you start over here, because you got to fill in to the left. And so I'll say, okay, 1, 2, 3, 4, like that. I'll fill those in with zeros. And then rewrite it with the decimal in the correct place, like that. Or, if I want to do the counting without doing loops method, I start with the last digit. I say, okay, well, that's my first, I don't start counting that. I start counting at the decimal place the same as I did before, but I'm going backwards. So I go 1, 2, 3, 4. You get the same answer, hopefully on a nice straight line, not up the hill like I just did, but just either way works fine. Any questions on going from decimals to, from scientific notation to decimal notation, or standard notation? That's the other word for this. You'll see it both ways, decimal or standard notation. No questions? Okay, going the other way, if we want to write something in scientific notation always has the same format. At most, 2 decimal places here. Never more than that for scientific notation. So we move the decimal from where it is at the end of the number. I'm here right now at the end of this number, and I need to come here so that I have the first box, a decimal, and then the second box. And in this case, those are all zeros, so I don't keep them. So I'm going to be 4.6. how many places I moved over. Now, this is kind of backwards from before, whereas before, if we were moving the decimal place from a negative exponent, we moved to the left. But when we're going from standard notation to scientific notation, if we have, basically, if you have a big number, positive exponent. If you have a long decimal, negative exponent. So this is going to be a positive 6. Give me just one. Okay, for the other direction, same idea. We want to move along until we find the first number that's not 0. And we put the decimal right after that. So here. And then I count how many places I have to move it. 5. And because it was a long decimal, I'm going to have a negative exponent, so I'm going to be 2.3 times 10 to the negative 6. So we can multiply or divide. Okay. Now, if you're multiplying in scientific notation, I keep reading the T. Okay. Okay, if you're multiplying, you multiply the decimal part, add the exponents on the 10, and then you might have to adjust it because if you multiply the decimal parts and it gives you the wrong format, the wrong number of decimal places, you have to move the decimal over, and I'll show you guys how to do that. And if you're dividing, you divide the decimal places, decimal parts. You subtract the exponents. And then make your adjustments. Okay, so to multiply 3.4 times 10 to the 9th times 2 times 10 to the negative 5th. Okay, the first step is to multiply the decimal part. So I'm going to do 3.4 times 2. So I'm going to get 6.8. Okay. The second step is basically I'm multiplying the tens part, but when you multiply common base with an exponent, you add them. Okay. This is my new decimal part. This is my new exponent. So the answer is 6.8 times 10 to the 4th. Now, before you go, that's really annoying and complicated. I want you to see what the multiplication would look like without the scientific notation. I don't know about you, but I don't know how to do that. I'd much rather do this. So if you, let's say just a hypothetical example of one going the other direction. So let's do 0, 3, 2, 1 times 10 to the 9th. Okay. I can't have 0.0321 times 10 to the 9th. It has to be the 3, has to be the first digit. It's going to move this 2 places. So I'm going to subtract 2. Okay, here I moved that way, so I add. Here I'm moving this way, so I'm subtracting. So this would be 3.21 times 10 to the 7th. Always has to be one number, one digit, decimal place, and then a maximum of 2 digits. It can be just one digit, but it can have a maximum of 2. Questions about that? How to adjust? You guys want to see a couple more of those? You're okay with adjusting? All right. Multiplying, except we divide and then subtract instead of multiplying and then adding. So I'm going to do 4 into 8.4 first. And then I'm going to do negative 7 minus negative 4. And whenever we subtract a negative, it's positive. So I get negative 3. That's my new exponent. So 2.1 times 10 to the negative 3. Questions on that? And that one, obviously, it doesn't have to be adjusted because my decimal's in the right place. These are the exponents on the 10. And you subtract the bottom one from the top one. So the top minus bottom. Make sense? Did I lose you?
No.
Okay.
Because it was, since it's double negative,
Yeah.
change it to a 5.
Negative 11 if it's negative 5.
Negative 5 minus 6.
Oh, okay, gotcha.
So, and then this one was 15 minus 43. Negative 9 minus 6. Yeah, it's only if the negative, if it was a negative exponent in the denominator, that it ends up being plus.
So wait, why is it negative 16?
16, because I had to move it over 1, so I have to subtract 1 more from this. So negative 15 minus 1 gave me the negative 16.
Okay. Yeah.
Okay, so you have the national debt is $10.8 trillion in 2008. At that time, the population is 306 million. So if you were to take the national debt and divide it up evenly amongst the population, that would be how much money we each owe.
How much what?
Money we each owe to pay off the debt, national debt. If you said like every single person was responsible for the exact same amount of the debt. So 10.8 trillion divided by 306 million. So I'm going to do the 10.8 divided by the 3.06. And that gives me 3.529 stuff, but that 9 is going to round up the 2. So I have 3.53 plus 12 minus 8 gives me 4. So that's my new exponent. Okay.
So 225 to the top, 224.
That means that in 2008, every single person in the United States would have had to pay $35,000 to pay off the national debt. And that includes infants, really, really old people. Hmm?
Who has $35,300 to just give to the government when they take our money?
Some people don't even make that much in 3 years.
Some people don't even make that much in a
And
year.
infants don't even make that much for 20 years at least.
Unless they're super babies.
This is dealing with addition and subtraction and geometric sequences deal with multiplication and division. Okay, so we're going to talk about if you're given an arithmetic or geometric sequence, so sequence of numbers, how to find the next couple in the sequence. And then we're going to talk about if I give you a sequence and say I give you 5 numbers in the sequence, I could tell you how to find, I say, what's the 43rd number in that sequence? You'll be able to find that number without actually writing out all 43 to get there. Does that make sense? Alright, a sequence is just a list of numbers that are related to each other by a rule, and it can be any kind of rule you want to make up. You can say, okay, you take the first number, you multiply it by 3, you flip it over, subtract 6 from it, and then square it, and then add 42, and then divide it by 7. If you want. I mean, the sequence can be any rules. Okay. The numbers in the sequence are called the term. Okay. The most famous sequence is the Fibonacci sequence, and the rules. Oops, wrong thing. The rule for the Fibonacci sequence is you take the first term, you list it again. You add the first 2 terms to get the third term, so 1 plus 1 is 2. Then you add these 2 terms to get the fourth term, second, third, so you add the 2 before it every time. So 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 will give us the next one. 8 plus 13 would give us the next one. 13 plus 21 would give us the next one, and so on and so forth. Okay. Now, a Fibonacci sequence doesn't have to start with 1. It can start with 2. You could say 2, 2. So 2 plus 2 is 4. 2 plus 4 is 6. 4 plus 6 is 10. 6 plus 10 is 16.
So
It's just a rule.
all the numbers are going to be even.
Yeah, if you start with an even number, you'll get all evens. If you start with an odd, you'll get both. But the Fibonacci sequence can start with any number. The most famous starts with a 1, but any series like this where you add the first 2 to get this third, and then you add the second and third, those are all Fibonacci sequences. Sometimes that kind of a sequence, we remember chapter 1 when we did pattern recognition, sometimes those sequences are harder to see. The sequences in this chapter are going to be all addition and subtraction, or multiplication and division. So you're not going to have like weird things that we had before. So if we look at arithmetic sequences, it's a sequence where each term after the first differs from the preceding by a constant amount. That means you add or subtract the same amount every time. Okay. The difference between the consecutive terms is called the common difference. So if I have a sequence, let's say for example, I start with a 2, figure out what's happening in this sequence. To get from a 2 to a 7, I add 5. To get from a 7 to a 12, I add 5. 5, so I'm adding 5 every time. So my common difference which is D. It's 5. Okay. And these will be all, that'll be the same, they'll be add or subtract every time. So if I can do another one, let's say, like that. To get from an 11 to a 7, I subtract 4, subtract 4, subtract 4. So D in this case would be negative 4. So with the arithmetic sequences, it's always going to be you add the same number every time, or you subtract the same number every time. You just have to find that out. First 6 terms of an arithmetic sequence with the first term is 6 and a common difference of 4. So we start with the 6, and then we add 4. 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 And we add 4. Okay. So first term, common difference tells me 4, so positive 4 means to add 4 every time. Not too bad. What time we get out of here? 1:40? All right.
Oops.
All right, so once we've got that, the next thing we can figure out is how to find a random one, okay? So if we said that the first term was A sub 1, that 1 just means first term, and my common difference is D. I take the first term and I add D, and then I add another D, and then I add another D, and another D, and another D, and you can see the D's are increasing by 1 every time. Okay? The second term is just a 1. The third term is a 2. So the number of the term has 1 less D. Okay? So in order to find the general, like if there's a formula, the nth term is this right here. So this would be like the 5th term or the 10th term. Guys, shh. Okay. This is the formula you need. And so if I want to find the 20th term, n would be 20. So the 20th term means n equals 20. I would plug a 20 in right here. This is my first term. And this is my common difference. So if we take that term that we wrote just a little bit ago with the 6, starting with 6 with 4 in between, 6 would go here, 4 would go here. And then if we wanted to know the 20th term, 20 would go right there. Or we could find the 100th term, or the 5,000th term.
Because the first term goes for A,
Yeah.
and then N would be 20.
And then D is the number in between each of them. So, does everybody have the formula written down? Because you're going to need this formula.
Yes.
Okay.
Why is it minus 1 again?
Because if you're talking about the second term, you've only added 1 D. See, the first term doesn't have any D's. The second term has 1 D. The third term has 2 D's. So the number of Ds is always one less than the number of the term. Does that make sense?
Okay,
Yeah?
yeah.
Okay.
Why is that, why is that in front of the D again now?
Because
When you
that's
did
how
the
many we
change-
multiply by.
You said multiply, okay, multiply.
Because when we add, we start with the first term, that's just A, right? And then we add one D to get to the second term, and then we add two Ds to get to the third term, and
Okay.
then three Ds, and then four Ds.
So
right?
it's multiplication and it's not adding like you were doing before.
Yeah, it's, I mean, it's adding, but you're adding that many of them all at once. So if we want to find the eighth term of a sequence, the first term is 4, and the common difference is -7. Okay? This is our A1. This is D. A, D. And that's N. Okay? So I'm going to plug those in. A sub 1 is 4, the first term. I want to know the eighth term, and my common difference is -7. So I start with 4. 8 minus 1 is 7, times -7. So I get -49 plus 4. So my, so here's my A1 is 4, right? That's the first term. I want to know the eighth term, so it goes there. And then the common difference is -7, so that's equivalent. Okay, so that's what I plugged in. Then it's just a matter of working the math. So I do my subtraction here, then my multiplication, then my addition. Let's do same problem, same sequence. We've got 4 and -7, but let's say I want to find the 43rd term. Same sequence. I'm going to put in the 4. 43 minus 1 is -7. Okay. So what we do is identify those first. Okay. That's N. First term, that's your A sub 1, and that's D. Okay. That's your formula. Why don't you guys try these 3? And then we'll compare answers. So an arithmetic sequence adds or subtracts the same number every time. The geometric sequence is a multiplication. It's technically a multiplication, but it can be a multiplication by a fraction, which kind of makes it a division. So you're going to multiply or divide every time. Okay. So if I go here, we have a common ratio. That's what we multiply by. We call that R. 1 times 5 is 5. 5 times 5 is 25. 5 times 5 is 100. 25 times 5 is 125. Times 5 is 625. Times 5 times 5 times 5. Here I've got times 2. 4 times 2 is 8. Times 2 is 16. Times 2 is 32. Now this one See, I'm going positive, negative, positive, negative. I'm multiplying by negative. So if you're switching signs like that, you're multiplying by negative. So 6 times negative 2 is negative 12. The negative 12 times negative 2 is going to be positive 24. Times negative 2 gives me negative 48. Times negative gives me positive 96. So our first term is still going to be the same. We still have A1 as our first term. Our common ratio is what we multiply. If we go, let's say we were the other direction, let's say started at 625. I'd be dividing by 5 every time. My ratio is going to be 1/5 because that indicates I'm dividing by 5. But we write it as a fraction because we want to write it as a ratio. But that indicates that you're dividing by 5. So whatever number you divide by, put a 1 underneath it, or one on top of it. So it can go, we can keep getting bigger and bigger because we're multiplying, or we can get smaller and smaller because we're dividing. 6 terms of a geometric sequence that starts with 6 and it has a common ratio of 1/3. That means we're dividing by 3 every time. Okay. So we start with 6. If I divide by 3, I get a 2. If I divide by 3, this is why the fractions come in handy. I can do 2 times 1/3, and that gives me 2/3. And then I can do 2/3 times 1/3. So basically what I'm going to be doing at that point is I'm multiplying the denominator by 3 every time. You see that? So then 2/9 times 1/3 gives me 2/27. And then, so that's 1, 2, 3, 4, 5, and then one more. 27 times 3 is 81. Okay. Does that make sense? So you can do divide by 3 or multiply by 1/3. Let's do another one. I'm not going to do another multiplying by number one because I think those are, you guys are all okay with multiplying by 10 every time or something, right? So let's do first term 14 ratio 1/7. Okay, so I'm going to, I don't want another 2. Let's do 21 as our first term. Okay, we'll start with 21. That's still going to give me a 2. Hold on. Is 21 divided by 4. Oh yeah, you're right, it will give me a 2. Okay, that, I was right when I was doing that. Okay. So I start with 21. I divide by 7, I get 3. Then I'm going to get 3 7s, and then I'm going to multiply the denominator by 7 every time. 49 times 7. Come on, math geniuses. 49 times 7.
343.
343. I understand.
So with 1, 2, 3, 4, 5. We need one more, so we do 343 times 7. And then 3 dots. Indicate that it keeps going. Okay,
Would the formula be the same except with just an R instead of a D?
no, hold on 1 second. I'm just gonna. So because I'm raising it to an exponent, I have my first term, I have my ratio of -2. I do 8 minus 1, so I do -2 to the 7th. That's 128, and then I multiply that by -4. So if I wanted to find, let's say my first term was 6 and my ratio is 1/2. And we want to find the 10th term. So that's going to be 6 times 1/2 to the 9th. So I do 2 to the 9th to get my denominator. It's 512, so that's going to be 6 times 1 over 512, which those are both even. So that's going to be 3 over 256. Yeah, okay, that one. So that would be our answer. So when you have a fraction like this, you take the denominator to that exponent. So the 9 goes there. Because 1 to the 9 is just 1. So homework tonight. She'll go online and get it eventually. I know it sounds like a lot.